Yeah, thank you very, very much. So what I like to do is I like to start out by telling you who I am and why I'm here. So I wrote a diploma thesis, a master's thesis, before some of you were born. And I used the classical invariants, so-called brackets, for carrying out some very concrete computations with matroids and convex polytopes. And I had read as a student that according to Felix Klein's Erlanger program, which was just mentioned in the previous talk, that geometry is invariant theory. So according to Klein, the definition of geometry, it's those properties of the coordinates that are left invariant under appropriate transformations. And I was very inspired by that. Then I met Rota, who had a huge influence on me. So I was a postdoc at the IMA in Minneapolis, one of the math institutes that existed long before this computer science institute. And it was fantastic to be there as a postdoc. I'm sure some of the postdocs here feel the same about the Simons. And one day, Dennis Stanton came to me and says, "You've been selected as the note taker. You've been volunteered to be the note taker for Professor Rota." So Professor Rota gave 2 lectures called Introduction to Invariant Theory in Superalgebras. Anyway, that led to a joint paper. So I have a joint paper with Rota with this title that nobody has ever read. Now, in the following year, in my second postdoc, I was in Linz, Austria. And actually, I offered a course. So I thought, now I really should learn more about invariant theory. So I offered a 1-semester course called Algorithms in Invariant Theory. And that was later published as a book in the RISC series. RISC is the Research Institute for Symbolic Computation, founded by Bruno Buchberger. And that's another advice to the postdoc. There's no better time in your life to write a book than as a postdoc. Now, my first regular job at Cornell, in the first year, there was a program at another institute that's been scaled down quite a bit since. DIMAX, by some measure, was the first theoretical computer science institute. And they ran their first program on computational geometry, and that's where I met Ketan. So both Ketan and I have a background in computational geometry, and then we sort of did other things since, and now we met again. So that's the brief personal history. So what's invariant theory? So let's fix a field K of characteristic 0, so such as the real or complex numbers. And I'm going to consider a matrix group G. So G is a subgroup of the group GLN of invertible n by n matrices. So G is not just an abstract group, but it's given as a group of n by n matrices. Now every matrix, little g, in the group gives us a linear change of coordinates on the ambient vector space, k to the n. And it also transforms polynomials. So the notation here is k x1 up to xn is the ring of polynomials in n variables, x1 up to xn, with coefficients in k. And here's the rule for changing coordinates. So every invertible matrix transforms a polynomial to a new polynomial. An invariant of G is a polynomial that's left unchanged by this transformation for every group element. So if for every group element little g in the group, the image of a given polynomial under this transformation is the same polynomial, then I call that polynomial an invariant. Now, if you have 2 invariant polynomials, you can add them and get another invariant. You can multiply them, get another invariant, and multiply by scalars and so on. So they form a subring. They form a sub-K algebra. And this is my notation, k x1 up to xn upper G. This is the set or subring of invariants. This is the invariant ring. So this is the subring, subalgebra we're going to be interested in. Now, everybody is familiar with one example of this, which is the ring of symmetric polynomials. So in this case, Sn is the group of n by n permutation matrices. That's a group of order n factorial. These are the permutation matrices. And for example, so we know that this is generated by the elementary symmetric polynomials. Since k is characteristic 0, it's also generated by the power sums. And concrete examples, so here we have the polynomial ring in 3 variables, and the invariant polynomials are generated as a k-algebra by either the elementary symmetric polynomials or the power sum. So if any other invariant polynomial walks into the door, along with Professor Christandl walks into the door, then we can write this as a polynomial in the elementary symmetric polynomials. And that representation in this example happens to be unique, but in general the representation may not be unique. Let's do another example. Let's take G to be the group of 2 by 2 matrices given in this set. So this is the set of these 4 2 by 2 matrices. So as an abstract group, this would be the cyclic group of order 4, but we are thinking about this as a group of matrices. Well, what are the invariants? Well, the first thing you notice, so I defined an invariant to be a polynomial that's fixed by any group element, but it suffices to look at generators of the group, right? So if you have generators of the group, if some polynomial is fixed by the generators, then it will be fixed by every group element. So this group is generated by a single matrix, for example, this one. So the invariant ring consists of all polynomials and 2 unknowns, such that if I replace y by x, and I replace x by negative y, I get the same polynomial. So here are 3 polynomials that have this property, x squared plus y squared, and 2 of degree 4, x squared, y squared, and then here a more interesting one, x cubed y minus xy cubed is also an invariant. Now I claim that these generate the ring of invariants. Again, if any other invariant walks into the door, we can write it as a polynomial in the 3 basic invariants, but that representation is not unique. In fact, there is a relation, there's an algebraic relation among these 3 invariants, so modulo that algebraic relation, it would be unique. So A is the quadratic, and B and C are the cubics. So if I think of A as an unknown of degree 2, and B and C as an unknown of degree 4, there's this relation of degree 8. And so the ring of invariants in this case is a polynomial ring, and A, B, and C modulo the principal ideal generated by that relation. So they are isomorphic.
Missing, or is that double slash a quotient or GIT quotient?
Yes.
So we could do the single slash it. Okay, good. I'm not missing anything.
So how should we think about the ring of invariants? So why do we look at these rings at all? Well, they are the ring of functions, the ring of polynomial functions on some space, and the space is the quotient. So in this example, if we look at K2 and we make a new space, we can make a new variety by lumping together everything in an orbit. Well, in this example, all orbits but one have 4 elements. And there's just the origin, has a lonely guy in the orbit. And then the orbits are parametrized exactly by solutions to this equation in this example. Okay. Now the question I'd like to address first is how can we be sure that there are no other invariants? You certainly agree that these 3 things are invariant. You easily check that they satisfy this as the generating relation, but maybe there's some other invariant out there that's not yet represented by these 3. How can we really be sure that these are all the invariants? Here's one more example where I'm using a group that's not a finite group, but an infinite group. So here I'm going to sort of shift gears a little bit. So let's look at K star, the multiplicative group of the field K, as an abstract group. Okay? So I'm going to take that abstract group K star and I represent it by 3 by 3 diagonal matrices. And that gives me a 3 by 3 matrix group. And I'm going to write this by telling you how it acts on polynomials. So T is a non-zero scalar. And then the action is, well, you scale x by t squared, y by t cubed, and z by 1 over t to the 7. Right? So that's an action that's given you explicitly, infinite set of 3 by 3 matrices that as a matrix group is isomorphic to the abstract group K star. And I'm interested, which polynomials are left invariant under this action. Well, for monomials, it's sort of easy, right? So this is, as a vector space, it's generated by monomials that are invariant, right? This acts diagonally. So as a k-vector space, I have to look at monomials x to the I, y to the j, z to the k, such that 2i plus g 3j is 7k. And again, you can calculate a finite list. In this case, there are 4 monomials listed here. You quickly see that these are invariant, and I claim that they generate the ring. Every other invariant will be a polynomial with coefficients in k in those. Now, is it true that the ring of invariants, so S is short for the polynomial ring, so is it true that the ring of invariants is always finally generated? That's a basic question. So we'll answer this question today. Well, for example, if we have such a scaling action, well, then the problem boils down to solving a linear system of equations over the non-negative integers. But it turns out that the semigroup or monoid of non-negative integer solutions to a linear system of equations is always finally generated. So if G is an algebraic torus, the answer is yes. So every semigroup, so in this case we're looking at L as a linear subspace, namely the plane given by this equation. We're taking this linear subspace and we're looking at non-negative integer points on it, and that's finally generated as a semigroup. And there's very fast software called Normalies that will calculate this for you. Okay? So if you're given a linear subspace L, you can calculate this finite set, the so-called Hilbert basis, quite rapidly. Now the answer to the blue question is also yes, if G is a finite group. So if G is a finite group of n by n matrices, then the answer is also yes, and I'm going to prove that to you in a moment. So let's talk a little bit about finite matrix groups. So one thing that you can do with the finite matrix group is you can take the average over the orbit of a polynomial. So if P is a polynomial, I'm going to write P star for the average of all elements of all transformed polynomials in the orbit. So I take 1 over the order of the group, and then G of P is the transformed polynomial, and this is a finite sum. It's legit to divide by the order of G because the characteristic is 0. Okay? So in this talk, 3 is never 0, so therefore this is well defined. So I get a map from S to the ring of invariants. So I take a map, takes any polynomial in S and makes an invariant in SG, and that's called the Reynolds operator. Well, what happens? So the world expert on this topic happens to be in the audience. Gregor, where are you? There's Gregor. Okay, so I wrote a so here's the thing. Your postdoc, you write a book, chances are it's pretty bad. Okay? But the good thing is that experts like Professor Popov and others look at it, give you feedback, and eventually, a couple years later, somebody will write a real good book. So the good book was written by Derksen and Kemper, and Gregor in particular is an expert on finite characteristics. So maybe I'll defer you.
Well, there's certainly no Reynolds operator, and things do go wrong. Finite generation still is true, but the calculation is harder and the structural properties are much worse. So everything that may be bad does happen in the case with the characteristic divisor group.
Okay. Now the Reynolds operator, which we have under my hypotheses, has the following 3 properties. A, it's a k-linear map, right? So if you take just a linear combination, right? So the average of 2 polynomials, if you take the sum of 2 polynomials, then the average is the sum of the averages. Right? That's clear. First of all, if you start already with an invariant polynomial and you average, you get that same polynomial back. Right? So on the subring of invariance, the Reynolds operator is the identity. Right? The average of an invariant is that invariant. And the last property C is the following. It's an SG module homomorphism. So in English, if P happens to be an invariant, and you multiply it with a non-invariant G, and then you average, well, you could do it the other way around. You could first do the average and then do the multiplication. Okay, so that's the last property. So if P is invariant, Q is anything, then the star of their product is P times Q star. Okay, so that's equivalent to saying that the Reynolds operator is a modular homomorphism over the invariant ring. Oops. Now, it could happen, right? It might happen that for some group G that's not a finite group, right? Some other matrix group might have this property too. So let's introduce an adjective. So I'm going to say a group of n by n matrices is reductive if such an operator exists. Right? So you have some infinite group maybe, but it could happen that there's some operator star that satisfies A, B, and C. I'm going to call that a reductive group. And then, finite matrix groups in characteristic 0 are reductive. Right? That's the remark we just said. So here's Hilbert's theorem. So in 1890, Hilbert proved that the invariant ring of a reductive matrix group is finitely generated. And I would like to give you the proof. I will give you the proof. Okay. So if you have a group of matrices, and that's reductive, so this includes all finite groups and some infinite groups. And if we have these properties A, B, and C, then the ring is finally generated. Well, we have to, use these three properties. So let's remember them, right? So this is a talk for the students. So remember A, B, and C. We want to use all three. Okay? Yes?
Doesn't number 3 imply C by both B and A? Just wondering.
Well, maybe A, yeah, maybe. But let me list them separately. Good. Somebody's paying attention. Okay. So here's the unique proof in this talk. Okay. So let's go through the proof. So, well, first of all, the invariant ring is a K-vector space, right? That's clear. It's a vector space over K. And it's spanned by the symmetrization of all monomials, right? So the polynomial ring as a vector space has a basis, namely the monomials. And so if every polynomial is a linear combination of monomials, but by property A, I can apply the star. So therefore, SG as a K-vector space is spanned by symmetrizations, Reynoldsizations of monomials. Now, among all of these infinitely many monomials, there's one that's special that I'm going to kick out. That's 1. Okay, so I'm removing, the monomial 1. So I look at all the non-constant monomials, and I write IG for the ideal in S that's generated by these. So IG is the ideal generated by all non-constant symmetrized monomials. Or equivalently, IG is the ideal generated by all homogeneous invariants of positive degree. Now, by Hilbert's basis theorem, proved in that very same paper for that very purpose, by Hilbert's basis theorem, the ideal IG is finitely generated. In fact, it's finitely generated by a finite subset of the set I gave you. Right? So I've given you an ideal in terms of an infinite generating set. Then this infinite generating set has a finite subset that generates the same ideal. Okay? So that's the basis theorem, proved in the same paper. So the ideal is generated by a finite set of invariants, and I'm going to call these invariants P1, P2, up to Pm. Now I claim that we're done. Okay, so I claim that these same invariants generate the ring of invariants as a K algebra. That's the set we want. Okay, that was Hilbert's argument. So, well, let's prove it. So we do what we teach our freshman discrete math students. We proceed by contradiction. Right? Suppose not. Okay? So suppose not, and pick a counterexample. So pick a counterexample, for example, of minimal degree. So I'm assuming that these guys, they're certainly, these are all invariants. So whatever this ring is, it's contained in the ring of invariants, but it may not be the whole thing. So maybe out there's some other invariant Q, and then, the positive integers are well ordered or something, right? So there exists one of smallest degree, Q. Okay, well, Q is certainly in the ideal IG, right? So IG is the ideal of all homogeneous invariants of positive degree, so Q is in there. And since P1 up to Pm generate this ideal, we can write Q as a linear combination, F1 plus P1, blah, 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 plus F1 times Pm, where the Fi are some polynomials. Now, furthermore, by looking at the degree, we can assume that these multipliers, Fi, are homogeneous of complementary degree. So the F's and Q have strictly positive degree. And then, the multipliers Fi can be chosen of complementary degree. So F2 can be chosen of as degree, whatever the degree of Q is, minus the degree of P2. So now we're going to apply properties B and C, and as Jesko pointed out, it's really all property C, right? So now we're going to apply the other properties. So this invariant Q is equal to Q star, because it's an invariant. Now we're going to plug in, we use the property C, so it's F star times P1, blah, 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 up to Fm star times Pm. But what does this say? Well, now I've written Q as a linear combination of the same generators, but now the multipliers are invariants of positive degree. So therefore, each Fi star now is an invariant, but its degree is strictly less than the degree of Q, and we're done, right? So that's a contradiction, right? By the minimality assumption here, up there, each Fi star is already in the subring generated by P1 up to Pm, and that contradiction proves the theorem. Okay? So that's it. That was Hilbert's argument, and as Ketan said, some people thought this was theology.
Theology was the proof of the basis theorem.
The theology is here, right? The theology is in the basis theorem. So how are you going to make these generators? How do you find the generators, right? From some, if you've given the matrix group, how do you actually do this? So we'll talk about this in a moment. Okay, so that's Hilbert's theorem. But before we go on, let's make a few more comments about finite groups that make this more precise. So Eminerto in 1916 gave a degree bound, actually. She showed that for a finite group, again under my hypotheses, all you need to look at is polynomials of degree at most the group order. Right? So the ring of invariants is generated by polynomials of at most the group order, and then in particular that would also give you finite generation. That's a separate argument that she gave, and we've seen already one example where this bound is tight. Right? So the group of rotations by 90 degrees. So if we rotate by 90 degrees, that's a group of order 4. We had 2 minimal generators of degree 4, so this is tight in general. Here's another one that I like a lot. So this is Moline's theorem from 1897. So one reason I can't talk to the experts in the room in this tutorial because most of them are dead. So Moline in 1897 calculate the Hilbert series of the ring of invariants. Right? So what's the Hilbert series? So by definition, you can make a generating function in an unknown z, where you sum up z to the d, and the coefficient of z to the d is the k vector space dimension of the dth graded component. So this is the vector space of invariants homogeneous of degree d. It's a finite dimensional vector space, and we just record its dimension, these dimensions in a generating function, and this is well known to be a rational function in Z. But Moline gave an explicit formula, namely it's the average of the inverted characteristic polynomials of all group elements. And what I'm going to do in my characteristic polynomial, usually you write matrix minus Z times the identity, but I'm going to switch the Z. Okay, so slightly modified characteristic polynomial. So I look at any matrix in the group. I look at this modified characteristic polynomial, so the identity matrix minus Z times that matrix. 1 over it is a rational function, and then I take the average of these rational functions. That's a rational function, and according to Moline, this is the Hilbert series. Okay? That's a very useful trick because it allows you to calculate the enumerative properties, the Hilbert series ahead of time without actually calculating invariants. So let's look at this in my example. So if my group is generated by rotation by 90 degrees, right? So then here I have these 4 characteristic polynomials. So this bar just means the determinant of this matrix. Then I take the reciprocal, I add it up, right? And then, I get this rational function that has this very suggestive form, 1 minus z to the 8 divided by a product of 3 things. And, experts in this game, they will suspect, that there are, maybe I got this, maybe there's a typo. Anyway, so by looking at this, you can suspect, what the degrees of the generators and the ABC relation might be. Klim?
Do you know how to calculate Hilbert series for all reductive groups or only for finite?
Well, on this slide, we're doing it for finite groups.
But it's known how to do it for all reductive.
Well, let's get there. Okay, so here I gave a formula. Of course, if G is a big group, right, then you can ask the question how to evaluate the sum rapidly. So let's do the sum here for a moment. Anyway, so then, I get this generating function. So this says there are 3 linearly independent invariants in degree 6, but there are no invariants in degree 5, for example. Okay? So we know that ahead of time, and that can guide the calculation. I'm going to give you 2 algorithms. So the first one I'm going to call the Crude Algorithm, okay, for calculating the invariance of the invariant ring of a finite group. Okay? So step 1, calculate the Moline series. Right? So sum over all matrices in the group and average the inverted characteristic polynomial. So now we know the Hilbert series as a rational function. Then you make a bunch of invariants of low degree using, the Reynolds operator, right? You list your 37, first monomials you like, you take average, and you have a bunch of invariants. Often you'll get 0, right? Often you get duplicates, but you just make a bunch of invariants. Well, then you calculate the Hilbert series of the current subalgebra. So you have a bag of invariants in your hand. Using implicitization, Gröbner bases, Bertini, whatever, you can calculate the Hilbert series of that subalgebra. Right? That's a rational function. So it's the algebra generated by the invariants you now have. Okay? Well, it might happen that you're very, very lucky. Namely, it might happen that that rational function equals to the other pre-computed rational function as rational functions. Well, if that happens, we're done. Well, why is that? Well, both the invariant ring and the current subring are graded K-algebras. In particular, they're graded K-vector spaces, where each graded component has a finite dimension. Right? Now we're using the following principle. If you have a finite dimensional vector space contained in another finite dimensional vector space, and if those 2 vector spaces have the same dimension, then they're the same vector space. Okay? People are smiling, right? But that's an important fact. So based on that, we're done. Okay? Now, if you're not done, you go back and make more invariants. Okay? So that's the Crude algorithm. If you have a degree bound, that's an actual algorithm, and otherwise it's a heuristic. Now, let me give you another algorithm that was invented by Harm Derksen in 1999, but it should have really been invented by, Gordon and Hilbert. And it goes like this. You introduce 3 sets of variables. So the input to the algorithm is a matrix group, maybe a finite group of n by n matrices. And I'm going to introduce 3 sets of variables. First of all, the nx variables. N is the dimension of the space, the ny variables. And then I'm going to also make variables for the group. Right? So the group is a finite group. It's going to be infinite in a moment, but it's a finite group, so it's a finite subset in the space of n by n matrices. So in particular, it's a variety. Right? So every finite subset of the n squared dimensional vector space over K. So I'm going to write down equations. I'm going to cut out my group elements by a bunch of equations, G1 up to GR and n squared unknowns. Okay. I'm sorry, G is, so I'm writing G for the coordinates, and then, the equations I'm going to just call this. So G and G, this ideal is the equations that cut out the group. Okay, now I'm going to do the following and look at the following ideal. So look at the n coordinates of y minus gx. right? So let G act on X, the vector X, and I want to say it's equal to Y, right? So this is n polynomials. I throw in the equations of the group. So this is an ideal J in a polynomial ring in 2n plus r unknowns. And I've given you generators. Now I'm going to eliminate the group G. So I, for example, put a lexicographic term order that makes G1 up to GR very expensive, and the X is cheap and desirable. And then you calculate the elimination ideal. So I take this ideal, and I intersect it with the subring generated by the X's and the Y's. So now I have a bunch of polynomial in X's and Y's. And now I'm going to get rid of the Y's. I just set Y1 up to Yn 0. So now I have a bunch of polynomial in the X's.
A little confused what these G's are.
Okay, so G
G1 up to GR are...
is a vector. No, it's a vector. I'm sorry. So G represents a group element.
Okay.
So, for example, I could take R to be n squared. Right? So I just make one unknown for every entry in my matrix. And then this is, whatever equations I have. So this is just the ideal of the algebraic group, which in this case is a finite group. Okay. Well, now and then I have P1. I just average them and they generate. Okay. So according to Derksen, the averages P1 star up to PM star, will generate the ring of invariants. Okay. So let's see a small example, just a practical example. So we had the torus action. So we acted on three-dimensional space. So what's the role of this? In geometry, what we're saying, we're looking at triples, right, of 2 points in the space, of a point and another point, and a group element that moves from one to the other, right? So in particular, this ideal, this parenthesis ideal, is the variety, represents the variety of pairs of points that are in the same orbit. Okay? And then I eliminate Y. So here's a small example. So my group is the torus K star. I'm introducing, this characterizes this group. So I'm introducing two variables, S and T, and the equation S times T minus 1. Right? So that describes K star as an affine variety and as a group, as an algebraic group. Right? So, and then, I have this part over here. This is n equals 3 equation. So U minus T squared X, V minus T cubed Y, W minus S to the 7th Z, right? S is the inverse of T. And now you get your device and you say Gröbner, right? And you do this and you get the generators we had on this couple slides ago. Okay? Okay. Now, what about classical invariant theory? Of course, Hilbert was interested in finite groups, but he was even more interested in the general linear group and the special linear group. And those are the kind of groups that we heard in the previous talk, and we'll hear much more about this week and the rest of the semester, and that was the group that was on your mind. But of course, now we need maybe a moment to talk about representation. So what I said so far is we're taking groups of n by n matrices, and I'm continuing. In the rest of this talk, I will continue to look at matrix groups. So I'm going to write D for the SLD. So SLD is the special linear group. These are D by D matrices with determinant 1. That's an abstract group. So I think about this as an abstract group. So I take the abstract group, SLD, and I represent it as a matrix group acting on a big space, an n-dimensional space, and the map rho that does the representation will be assumed to be a polynomial representation. Okay, so rho is a polynomial function that maps D by D matrices and makes n by n matrices. And in this example, it's actually equivalent to assume they're rational functions. Okay, but let me assume they're polynomial functions. So rho, the representation, is given to you by n squared polynomials in D squared unknowns. It'll be a pop quiz very soon. Okay? So rho is given to you by n squared polynomials in D squared unknowns. Now the fact that Klim was asking about is this group reductive? Yes, this group is reductive. So for this group, there is a Reynolds operator. And it's actually interesting. So what is the Reynolds operator? How do you realize it? How do you average over this group? And there are different strategies for doing this. So there's sort of maybe 3 different ways of doing this. The classical way, attributed to Cayley, is something called Cayley's omega process. So Cayley's omega process is a sort of a differential operator that carries out the averaging for you. Okay? Well, if you're more into calculus, you can take the sum that I had in the definition of the Reynolds operator and think of it as a Riemann sum and turn it into an integral. Right? So somehow we want to, rather than summing over this group, we want to integrate over this group. Well, that doesn't quite work, right? So we have to pass to a compact subgroup. So integrating over the appropriate compact subgroup is another instantiation of the Reynolds operator. And there are more. So there are 3 or 4 different ways of carrying out the Reynolds operator. Let's do an example. Let me take D to be 2 and N to be 4. So the abstract group I'm talking about is the group of 2 by 2 matrices with determinant 1, okay? Which I think of as a hypersurface in a 4-dimensional space. Right, so in a 4-dimensional space with coordinates x11, x12, x21, x22, I have a hypersurface given by saying this times this minus that times that is 1. And that's a group. That's an abstract group called SL2. Now I'm representing this abstract group in a 4-dimensional vector space. So now I have a 4 by 4 matrix, and my map rho is given by this formula. And the particular situation that this describes is the adjoint representation. So X is a 2 by 2 matrix. So I'm acting with the abstract group SL2 on the concrete vector space of all 2 by 2 matrices, and the action is conjugation. Okay. So the action is you take an invertible 2 by 2 matrix with determinant 1, and it acts on a 2 by 2 matrix by this formula. Now, this doesn't look like a polynomial, representation, but you can replace G inverse by the adjoint or adjugate, right? So you can replace this by the adjoint, and then this becomes a polynomial representation giving by a quadratic 16 quadratic monomials in 4 unknowns, G11, G12, G21, G22. That is the representation. Okay? Now another way of saying this, the vectorization of this 2 by 2 matrix. So this 2 by 2 matrix is a point in a 4-dimensional space. So if you write its coordinate as a vector of length 4, column vector of length 4, then you get that column vector of length 4 by multiplying this 4 by 4 matrix on the right with the column vector x11, x12, x21, x22. Is that clear? Students and postdocs, is that clear? That's how the representation works. It eats an invertible 2 by 2 matrix and it represents it by this formula as a 4 by 4 matrix. That's my matrix group. So my matrix group is the group of all 4 by 4 matrices that look like this. Okay, now what is the invariant ring in this case for the adjoint representation, or what functions are invariant? Right? Well, in this case, it's not so difficult. So what functions of a 2 by 2 matrix are left invariant under conjugation? Well, for example, the determinant. Right? So the determinant is a polynomial in the x's. And since G, by definition, has determinant 1, right, the determinant of x is an invariant. Another invariant is the trace, and they generate. So in this example, the ring of invariance is generated by a linear polynomial, namely the trace, and a quadratic polynomial, namely the determinant. Now, orbits play a big role in this workshop, so I should say a few words about orbits. So in the finite group case, we saw that the ring of invariants is exactly the coordinate ring on some variety, and the points of that variety were exactly the orbits. That gets more complicated, quite a bit more complicated for infinite groups. So let's, look at this example. So first of all, it's clear that the invariants are constant along orbits and their closures, right? So the invariants are polynomials, and by definition, along each orbit, an invariant will take constant values. And since everything is, these are polynomials, right? It has same values still everywhere in the limit. So these are going to be constant and orbit closures. Now maybe all the orbits are closed, right? In the finite group case, they were all closed. So let's look at, for example, let's pick a random 2x2 matrix like this one, 2, 3, 5, 7. And let's look at the orbit. I claim the orbit is closed, and closed in either the classical topology, if k is the real or complex numbers, or Zariski topology. It's closed in every reasonable sense, right? It's closed, and it's an algebraic variety. Namely, it's the variety given by two equations, namely trace is 9 and determinant is -1. Right? So the variety of these two equations in the space of 4x4 matrices is exactly the orbit. So this orbit happens to be closed. Now, since this is going to come up later this week, I'm sure, in this example, it's actually better to replace the determinant by another quadratic polynomial. It's a little bit the analog. These are sort of like the elementary symmetric polynomials, and these are sort of the power sums. It's better to, in this context, to replace the quote-unquote elementary symmetric polynomials by power sums. So you can replace the determinant by the trace of x squared. So trace of the matrix squared is 83. So in general, if you have these actions, the little theta quiver we saw in the previous talk, it's always traces of words in matrices that generate the ring of invariants. Now maybe all the orbits are always closed and the invariants always separate the orbits, right? That would be the nicest thing, but not quite true, right? So there's something called the null cone. Hilbert called this the Nullkegel, right? So namely, what do? You take the variety of our ideal. We had this magical ideal that we generated in Hilbert's proof, generated by all homogeneous invariants of positive degree. Now, in the finite group case, its variety was just the origin. But in the infinite group case, this could have lots of zeros. There could be many, many, many points on the space we're acting on where all homogeneous invariants vanish of positive degree. So what is this variety, right? These are all the matrices where the trace vanishes and the determinant vanishes. And these are the nilpotent matrices. So matrices of nilpotent, that are nilpotent cannot be separated. And here's a little linear algebra exercise, look at matrices like 0 and then this one. You write down a bunch of sort of Jordan canonical matrices, and they're all in different orbits, and you cannot separate them by invariance because every invariant of positive degree takes the value 0. Okay, brackets. So I started the lecture by giving you a few words about personal history, so I should tell you what are these brackets. Now, and back to Felix Klein. So let's say n is d times m, and the vector space I'm acting on is the space of d by m matrices. Well, our group, SLD, acts on this n-dimensional vector space by left multiplication. Right? So you have you look at the space of rectangular matrices, and you act on it by left multiplication. Okay. That is a representation of the abstract group SLD. So that representation is given to you by MD times MD polynomials in d squared variables, which together form the representation rho. Now, the invariants are exactly the brackets. So the ring of invariants in this case has m choose d generators, namely the d by d minors of the rectangular d by m matrix. That's sometimes called the first fundamental theorem of classical invariant theory. Well, there's also a second fundamental theorem that tells you the analog to the ABC relation. It tells you the relations that hold among the generators, and they are also well known. There's a well-known system of quadratic relations known as Plücker relations. So I'm going to write this symbol, bracket I1, I2 up to ID, for the d by d subdeterminant given by the column indices I1 up to ID in my rectangular matrix. Okay, these are M choose these symbols. For example, if D is 2 and M is 4, there are 6 generators, bracket 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, and there's one relation. It's the quadratic Plücker relation. Now this is kind of nice. You can do geometry with this, right? That was Klein's point, right? Whatever you can express in these brackets should be somehow geometric. So suppose we have some geometric property, namely the property for 6 points in the plane to lie on a conic. That's a geometric property. So, well, if D is 3 and N is 6, right, then our matrix X, the 18 coordinates in our matrix, represent homogeneous coordinates for 6 points in the plane. And they lie on a conic if and only if this bracket monomial equals that bracket monomial. Okay? So whenever you have geometric properties involving various shapes and projective space, you can write down blue polynomials in the brackets that represent those geometric facts. Now, the vector space that we're really interested in, that we really want to act on, is the space of symmetric tensors, or the space of homogeneous polynomials. So I'm going to write SD, k to the m, for homogeneous polynomials of degree d in m variables. That's a nice finite dimensional vector space. In balls and boxes, many monomials generate this. There's the formula d plus m minus 1, choose m minus 1. That's our n. And the abstract group, SLD, acts on this vector space by change of coordinates. So we have a representation rho that eats d by d matrices and makes n by n matrices. Now, since the group is reductive, the invariant ring is finally generated, and the generators express geometric properties of homogeneous polynomials. Now, what's the point of these homogeneous polynomials? Well, they cut out hypersurfaces in the projective space. Right? So that was the motivation for Hilbert and his contemporaries. They wanted to know what are all the properties that a hypersurface of degree d in a projective space of dimension m minus 1 have. Can we have a finite alphabet somehow to talk about these geometric properties? So this is the point of departure for a more modern theory called geometric invariant theory, and I think Laurent will give a tutorial on geometric invariant theory this afternoon. I'm going to give you sort of 2 examples. So the first example is high school example. So let's say d and m are 2. So I'm going to look at homogeneous polynomials of degree 2 in 2 variables. They form a 3-dimensional vector space V. So n is 3, so that's the space of binary quadrics. So it looks like this: x1 t to the 0, blah, blah, x3 t1 squared. So I have a 3-dimensional space with coordinates x1, x2, x3.
So the group is SLM.
The group is SLD, I hope. I meant it to be SLD, right? So I claim that, so in this example, m is equal to 2, is equal to d. So SL2 acts on the 3-dimensional space of binary forms. Did I make a... Did I?
The first line.
Oh, I see. This should be m and n. Okay. So there's a typo. Okay. This doesn't work. Okay. Maybe up here. Okay. So there's a typo. Okay. So this should be, what are we doing? S, M, K, no. You switch M and...
should be SLM.
Okay. SL, no, I would like to stick with SLD. Okay. Sorry, guys. Confusion of indices. But I think you're going to get this example, especially after doing the pop quiz. Okay. So I will follow the Institute's suggestion to take a break during a long lecture. So we're going to take a 3-minute break. And in this 3-minute break, you are asked to write down the 3 by 3 matrix, rho of G, right here, and you will have glory forever by being the first to write this down. We'll take a 3-minute break for you to write down a 3x3 matrix. Over there, on the whiteboard.
1 minute per row. Do you know what else? Go for it. You first.
Have a marker. Do you mind if I write shot?
Go for it, Luke. And that calls for a big round of applause for Luke Erdin. Yay! Any questions? Maybe this is a good moment to ask for questions. Comments? Is this clear? So Luke wrote down a representation of the abstract group SL2 as a matrix group, a group of 3x3 matrices. In the set of these 3x3 matrices where A, B, C, and D are any scalars such that AD minus BC is 1, that set of 3x3 matrices is the group, and that group acts. And down there, it's ring of invariants.
The basis you take is a space of polynomials.
I took the same basis that Bernd did.
He did it on the slide. He chose the basis on the
Yeah,
slide.
I
that's
took the
right.
basis Bernd did.
Jesko, in my life, I have never, ever, ever chosen the basis. They always came to me. Okay, let's go. Okay, so in this case, you know from high school, right? You know the formula for writing down the roots in terms of the coefficients, and then the thing you take the square root of is the discriminant. x2 squared minus 4x1 x3. This single polynomial generates the ring of invariants. This is the generator for all geometric properties. For geometric statements you can make about 2 points on the line. Right? So if this group sort of carries the geometry, right, you talk about properties of 2 points on the line, and then, well, the interesting property is when do 2 points come together? When does this zero-dimensional variety, subvariety in P1 become singular? Well, if and only if the discriminant vanishes. Okay, let's do something slightly more interesting. Let's talk about ternary cubics. And I hope I get my D's and M's a little better, but okay, bear with me. In any case, they're the same again. So D and M is 3. So I'm interested in cubic curves in the projective plane P2. Okay, so a ternary cubic is a polynomial homogeneous of degree 3 in 3 unknowns, T0, T1, and T2. And the coefficients x1, x2, up to x10, they are the coordinates on the 10-dimensional vector space V we're acting on. So V is the 10-dimensional vector space of ternary cubics with coordinates x1, x2, up to x10. So we're interested in polynomials in these 10 variables. And we're interested in the ring of invariants. So with a little guidance from Luke, you can write down a 10 by 10 matrix whose 100 entries are cubic polynomials in 9 unknowns. And then that matrix group has a finitely generated invariant ring And in this case, you require two generators. There are two classical invariants that generate the ring. Okay? So the first invariant, called S, is a quartic. So this is a degree 4 homogeneous polynomial in x1 up to x10 and has 26 terms. Okay? Now that's an important remark, right? Because the space of quartics in 10 variables is a big space. Right? It has a larger dimension. But among those many monomials of degree 4 and x1 up to x10, only 26 run for competition. Only 26 have the right homogeneity, multi-homogeneity properties to have a chance to appear in an invariant. And there's a unique equation of degree 26, and this is known as the Arnhold invariant. Okay, so this is... Now what is the property? Well, for example, people interested in tensor decomposition will know that the Arnhold invariant vanishes if and only if my symmetric tensor has tensor rank at most 3. Okay, so typically if I take a random, excuse me? Tensor border rank. Tensor border rank. Okay, sorry. Yes, you're right. So I always just say rank. Okay, so tensor border rank, so any case. So this is the property that's S. And then there's another polynomial, a sextic T, and it has 103 terms. Okay, so the point I want to make is that these are very, very, very small polynomials relative to the total number of monomials of that degree. Now, just to sort of move this a tiny bit more towards algebraic geometry, right? So here's another invariant that you can express in terms of the basic invariants. That's the discriminant, right? So the discriminant delta is t squared minus 64 s cubed. So that has degree 12, right? So 2 times 6 and 3 times 4 is 12. So delta is a homogeneous polynomial of degree 12. Still pretty small. It has 2040 terms. And it vanishes if and only if the plane cubic has a singular point. So Ketan had this picture, right? So usually, okay, well, get these pictures, but if the picture is like this, that happens if and only if the polynomial delta vanishes. So that's very much a geometric property. Now, if delta is not 0, then this cubic curve is a smooth cubic curve. And that smooth cubic curve, together with the point on it, is known as an elliptic curve. So the cryptography people who will be here next summer love elliptic curves. Now everybody, especially your number theorist friends, they really, really like the J invariant. The J invariant isn't quite an invariant in the sense I discussed, because it's not a polynomial, it's a rational function. Right? That's actually better, because that's a sort of a function on projective space. So what you do is you take s cubed, this invariant, you divide it by delta. So you have the ratio of two homogeneous polynomials of degree 12. So this is a well-defined rational function on the 9-dimensional projective space with coordinates x1, x2 up to x10. And that's called the J invariant. Now the J invariant serves as a coordinate. I'm cheating a little bit here. It serves as a coordinate on the moduli space. So a moduli space is a quotient space of a space that is a parameter space that parameterizes objects. So in this case, x1 up to xn is the parameter space of all cubic curves in the plane. But then if we take cubic curves modulo projective transformations, we get the proj of this graded ring, the invariant ring. So we have this graded ring where S and T have degree 4 and 6 respectively, and J is sort of a nice coordinate on that space. But more about geometric invariant theory at 2 p.m. today in Laurent's lecture. Let me come back to the picture. So this talk had exactly one proof and also had exactly one picture. Let me explain the picture. There's a very old theorem in geometry known as the Cayley-Bacharach theorem that says the following thing about 9 points in the plane. Suppose you have 8 points in the plane, P1 up to P8, and these are the white points. So you have 8 points, this one, this one, this one, this one, this one, 8 white points in the plane. Then there is a unique ninth point indicated by the arrow with the property that every cubic curve through the 8 points must pass also through the ninth point. Okay, that's the Cayley-Bacharach theorem. Very nice theorem. So, you know, I mean, suppose you start with the two cubic equations, maybe the red equation and the blue equation, right? By Bézout's theorem, they have 9 common solutions, right? Well, then you can replace either blue or red by any linear combination, and you still, you know, have, I'm sorry, so say this again. You take any other cubic that also goes to the 8 points, it must necessarily go through the ninth point. Okay? This is a very old, easy theorem. It's actually very fundamental in the current interest work of Greg Bleckerman in particular on the connection between semi-definite programming and polynomial optimization. So there are 2 people in our program, or maybe at least 2 people, Greg and Pablo Parillo, who connect our program to the concurrent program. The concurrent program has a workshop next week on issues related to semi-definite programming, and that sort of plays a certain role in this topic. Now this is old, there's something new. So I wrote a paper with Jürgen Richter-Gebert from Munich and Chunchang Ren recently, which we submitted to the Math Monthly. And we solved the riddle that's been around for a little while. What's a good way of writing P9 in terms of P1 up to P8? Right? So by the statement, you can argue that there is a rational function. There's a rational expression for the ninth point in terms of the 8 given points. And there's an explicit formula in terms of brackets. Brackets, so these are the brackets. Oops. What happened? Brackets like this one. So there's, you know, a bunch of expressions like this that give you the coordinates for the ninth point in terms of the 8 points. Okay, any questions? So I think I have 16 minutes left. So I will be done well before the end of my time. Any questions?
What's the formula look like?
Not too bad. It's a short paper, you know. It's very, I mean, we write the formula. Okay, let me talk about finite generation. So we saw that for a finite matrix group, the invariant ring is always finally generated. I gave you the proof. And if you have a reductive group, for example, SLD, if you knew how to realize the Reynolds operator for SLD, I also gave you a proof, an algorithm for finding generators for SLD. So the question was, what about arbitrary matrix groups? Suppose you have an arbitrary group G of n by n matrices. Is the ring of invariance always finally generated? Right? Does Hilbert's theorem from 1890 extend to non-reductive groups? Now, why is this a meaningful question? Right? So if you maybe saw the proof, you said, well, what's the point? Right? The ideals are always, you can form the same ideal. Right? You could look at the ideal of all homogeneous invariants of positive. It's still finally generated. Right? And maybe its generators, symmetrized, still generate the ring of invariance. Well, that would be true, except you can't symmetrize. Right? Non-reductive means you cannot symmetrize. That's the whole point of not being reductive. Okay? Now also, we're not talking about ideals. We're talking about K subalgebras, right? A subalgebra of a polynomial ring need not be finally generated. So, for example, if you have a polynomial ring in 2 variables, x and y, and look at the x, xy, xy squared, so they generate a subalgebra, and that's not Noetherian. Right? That's it. You need them all. That's not a finally generated subring. So what about? So this was one of the open problems stated by Hilbert in the 1900 International Congress, and if students at Berkeley are unfortunate enough to have me in their German language exam, they either get Felix Klein's Erlanger Programm or they get to pick one of the Hilbert problems to translate. Okay, so a negative answer was given 60 years later by Nagata in 1959, and so there are groups, matrix groups, where the ring of invariance is not finally generated. So what I like to do in the remaining time, I like to describe a version of Nagata's counterexample And the exposition I'm going to give is, notation is coming from this paper, Sogby base of Cox-Nagata rings. Okay, so I'm going to give you an example now of a matrix group whose invariant ring is not finally generated, and then the talk is over. Okay, so that's the plan for the remaining time.
Good structure for all non-reductive groups for generators.
Jan is gone. Okay, he's giving a talk at 1 o'clock. Jan will speak in the combinatoric seminar. Well, they tend, I think the answer is yes. Do you know? So they're essentially additive groups. So multiplicative, if you take K star, versions like K star, they are reductive, but if you take additive groups, they tend to be not reductive. I can't answer off the top of that, right? So there's maybe experts over there.
Could you just repeat the question?
Oh, the question was, is there a structure theory for non-reductive groups? Can we classify non-reductive groups? Okay, let's look at one example. So we haven't, so let's...
Unipotent. There's always something unipotent at the bottom. As you said, a unipotent is a composition series of additive groups. So the additive groups are at the heart of it.
Okay, guys, let's see an additive group, okay? So let's do the following. So n, the space I'm acting on, is an even integer. So n is 2 times m, an even integer. And let me start with the additive group of the m-dimensional vector space. I'm going to take k to the m, so that's a vector space. And by vector addition, that's a group. So let's start with that group. Okay, I'm going to pass to a subgroup in a moment. Now that group has a representation in terms of 2m by 2m matrices as follows. Very simple. And it's going to act on a polynomial ring in 2m variables, x1 up to xm, y1 up to ym as follows. It does nothing on the x's. Okay? It fixes the x variables. But it takes the y variables and it shifts them as follows. So yi gets mapped to yi plus ui xi, and ui is the ith coordinate of the group element u. Right? So you give me, a group element which is a vector u, and then so your u, I can write as a 2m by 2m matrix, and then that's what it does. Right? It's sort of looks like an identity matrix with a little bit of stuff above the diagonal. Very harmless looking action. Now I'm going to twist this as follows. I'm going to fix an integer d less than m, and I pick a random d by m matrix u. Okay? So random means, well, whatever, random. Outside is a risky closed set. So I pick a random d by m matrix. Okay? And G is the row space. So G is a d-dimensional vector subspace of k to the m. Still a group, right? So the group I'm going to use is the subspace spanned by the rows of U. So as an abstract group, that's k to the d, right? The additive group k to the d, but I'm going to use it, comes from a matrix U. Okay, so as an abstract group, this is k to the d, and it acts on the polynomial ring in 2m variables by the same rule, right? So I just keep the action. That's my example. Is that clear? So it's very clear, right? So I take KD, all I need is the matrix U, and you can write down with a little help from Luke, right? And 2m by 2m matrix whose entries, depend on big U and little u. Okay, so let's see an example. Oops. Take the punchline away. So how could you make invariants? Well, you could do the following trick. You take the matrix U and you add one more row. You add the row y1 divided by x1, y2 divided by x2, and so on. And then you clear denominators. You multiply on the left with the diagonal matrix x1 up to xm. Okay, so this is now a matrix of size d plus 1 times m, and it has linear entries, right? In the first d rows, it has linear entries in the x's, and in the last row, you just have y1 up to y. Oh, maybe there's a typo. Sorry, guys. This is a ym divided by xm. Okay? So I take yi divided by xi, and this just clears the denominators. It multiplies the ith column by xi. Okay. So if the parameters are very small, so for example, if m minus d is 2, then they generate. So these invariants, so the maximal minus, okay, so what are the invariants? So first of all, we have x1 up to xm. Right? They are invariant. Right? That's, everybody saw that, right? x1 up to xm are invariant. And I also claim that the maximal minus, the d plus 1 times d plus 1 minus of this matrix are invariant. And that's by the rule that you have a determinant. It doesn't change if you add a row, to another row. Right? So if you take one of the early rows and you add it to y1 up to ym row, the determinant doesn't change, and that just says it's an invariant. Okay? So if the parameters are really, really small, then these invariants, Cynthia, you look puzzled. Is it clear? No, it's clear? Yeah, so for small parameters, they actually generate. Okay? These invariants generate. But I claim, in general, they do not. So I claim the ring of invariants is not finally generated if the following holds. For example, if m is d plus 3 and m is at least 9. Okay? So if the difference m minus d, if the codimension of u is 3 and the ambient dimension is 9, then this is not a finally generated ring. Okay? That's the example. Ooh, I think you don't need characteristic 0. Yeah, well, you have to be a little bit careful what we mean by generic. So you certainly don't need characteristic 0, but maybe you want to avoid small characteristic. Let me put the proof idea, and then we'll discuss. Maybe Giorgio knows. I don't know about Del Pezzo surfaces over the 2-element field. Okay, I don't know. Okay, so maybe characteristic 2 and 3 is bad, but.
Have zero example, or
It's the same example.
okay.
That's the example. Yeah. So this is a variation on a theme of Mukai. Okay, so here's the proof. Okay, what you do is you blow up points in the plane. So P2 comes from the 3. Okay, and what's U? Well, U really specifies m points in the plane. So U is a 6 by 9 matrix. Okay? So that 6 by 9 matrix, its row vectors are perpendicular to a 3 by 9 matrix. And the columns of this 3 by 9 matrix are the homogeneous coordinates of 9 points in the plane. 9 random points in the plane. So the rows of U, that's a Gale transform, the Gale dual of 9 points in the plane. The linear relations among the 9 vectors representing 9 points in the plane. Well, if you blow these 9 points up and you do some classical geometry, the surface you get has very, very many symmetries. Okay? Well, first of all, it has the symmetries Sm. The symmetric group of m letters acts on this surface, right? Because you blow up these points and they're, it doesn't matter how you label them. So this whole situation is certainly symmetric under the relabeling of the points. But that's not enough. There's more symmetry. You can attach a little hook to the Dinkin diagram and you pass to a larger Weil group. And these are the Weil groups D5, E6, E7, E8, E9, E10, E11, and so on. So in each of these cases, you have a Weil group that's given by, picture like this, quiver maybe, something like this. But if you just have this row, you have the symmetric group, but you add, one little thing down here. That one little thing, that extra generator is called a Cremona transformation. So that extra generator, the Cremona generator, that is a beautiful thing, and you will discover these Weil groups. Now what about these Weil groups? Well, these Weil groups, they are given by generators and relations. So these are groups that are presented by generators and relation, and this is the picture. This picture is a system of generators and relations. Now, if you have a group that's given by generators and relations, this group may be finite or infinite. Right? And it so happens that it's finite up to 8, and it's infinite from 9 on. And that fact that the group is infinite translates into the fact that you cannot get away with finitely many generators. So I promised that I'll be done ahead of time. So here's the conclusion slide. So I talked about some very, very old classical invariant theory. I think it's a fun subject. It's timeless, and experts in this workshop will decide whether it's relevant. And maybe in Google Books thinks that I'm a co-author of Hilbert. Now, I started by talking about something that happened in 1984, and to the young people here, that was before you were born. That was probably, maybe you thought that Klein and Hilbert and I were contemporaries. That's not true, okay? So I'm not a co-author, so Reinhard Laubenbach and I, so Reinhard translated this, and I wrote an introduction. So this is a lectures in the Sommersemester 1897 in Göttingen. Professor Hilbert gave a course on the theory of algebraic invariance, and that's the book. Thanks for your attention. And I think we have time for discussion.
Questions or comments?
Okay, question? So in what sense does that extra node a Cromona transform? I mean, I'm not sure what you're meaning.
So this gives, maybe I'll let Giorgio answer. Let's make this more interactive. Where's Giorgio? Giorgio, this is Giorgio Ottaviani, and he will tell us about the Cremona action. Yeah, so what you can do, so if you have a configuration of, say, 8 points, let's make 6 points. That's everybody's favorite cubic surface, right? So suppose you have 6 points in the plane, labeled 1, 2, 3, up to 6. So what can you do? First, you can, change the labels. Right? That's one thing you can do. But here's another thing you can do. You can pick 3 of the 6 points and call them the coordinate points. So I'm so sorry, I made a choice. Right? So the first point is 1, 0, 0. The second point is 0, 1, 0. And the last point is 0, 0, 1. Okay? So then you take the Cremona map, which is called reciprocalize the coordinates. Right? So you take the coordinates x, y, z, and you map them to 1 over x, 1 over y, 1 over z. Okay? That's a nice map outside. So my 3 points span a triangle. They span 3 lines. And that's a very nice one-to-one, well-defined map outside that triangle of lines. But on that triangle of lines is a bit weird. So what it does, it maps the 3 lines to 3 points. And it blows up the 3 points to lines. Right? So the picture that you would see in a textbook looks something like this. So here is my 6 points, 1, 2, 3, 4, 5, 6. So maybe I pick these, and then, the image of this transformation. So 2, 4, and 5, they have perfectly nice images over there. But then, the lines become points, and the points become lines. So I get maybe 1 prime, 3 prime, 6 prime. And now I have a new labeled configuration of 6 points in the plane. So that additional symmetry acts on objects attached to my blown up surface, such as homology ring, and box ring, and all these.
Let's thank again.
You've only cut into the first speaker of the afternoon.
Just confused because you've been saying I was looking at you.
Oh, I'm sorry. It was 140. I'm sorry. 140? I remember you were the next speaker.
I also remember that.
I missed that. I'm not sure.